name is Lauren Nowak. I'm a second-year master's student in mathematics at San Francisco State. And to introduce my research, I want to set the stage with a kind of classical question from graph theory. So if you're new to graph theory, it's just the art of connect the dots. And I'm going to show you right here an example of a graph. Now let's suppose I have a box of crayons and I want to color in all of the vertices or the circles on this graph. But I'm going to have a particular rule. I don't want two of the same color connected to each other. So I don't want red connected to red. Here's one way I might have done it. But I'm a mathematician, so I don't want to just solve it one way and be done. Like, I want to ask more questions. And one question I might ask is, well, what are all the different ways that I might have chosen to color this? So now I need to do some counting, right? We're counting different ways. So I look at the vertex on the top and I have my whole box of crayons available to me. We'll say there's n of them. So I put an n there. I had n choices for that top vertex. And then underneath I had almost n choices, right? But I used one color already. So it's actually n minus one, right? I can't reuse the red one right now. If I move down to the bottom right corner, I actually again have n minus one choices. I can reuse the red now, but I can't reuse the blue. And then if I color in the yellow one last, I can't use red or blue, so I have n minus two choices there. And then if I want an expression that encapsulates all of those choices at once, we need to take the product. So we end up with what's called the chromatic polynomial of the graph. And this equation just literally encodes the information we just saw about the choices for colorings. Just a quick note is that edges are really important in this. If you take a look at this graph, and I just added one edge to it on the right, it actually changes the chromatic polynomial, right? Our choices changed, it becomes more connected. So how the edges are related to each other is a really important piece in this puzzle. So I'm going to show you a couple different graphs right here. And if you pause the video and take a look at them, there's actually a lot of different kind of nice structure happening here that you might notice. One property that I'm particularly interested in my research is something called log concavity and the unimodality of the coefficients. And I'll explain what that kind of second phrase means. Basically, what that means is if you take a look at the coefficients on this polynomial, you'll notice that they rise steadily and then fall off. So there's one peak number in the middle. For instance, for the one on the left, 1 rises up to 4, increases up to 5, and then falls back down to 2. This was a conjecture actually made in the 1970s that every single graph has this property of rising and falling like this. But it took several decades to prove. And I think it was in 2012 that Dr. Junha actually put out a proof of this property. So what my research does is prove this from a new perspective in a way that actually generalizes really nicely to some other settings, though I'm not going to kind of dig into that right now. And this approach actually focuses on volume. So what that means is I actually need an object to construct. And here's an example of one right here, where I've built it really carefully so that its volume and the way it interacts actually with a second object kind of encode information about the graph and its possible colorings. And I can recover the chromatic polynomial from this object. So if you're saying, like, how can we move from a graph to an equation to this, what's called a polytopic complex that has a volume associated with it, I really hope you'll take a look at the poster and come talk to me during the symposium, because I'd really love to share how all of these very different points of view actually have a common thread connecting them.